Hello students, in the previous lecture, two lectures, we have defined subgroup and we have discussed theorem based on union and intersection of subgroups. Now we'll define the product of two functions and then do theorem based on that. Let H and K be two subgroups of the group G. Then the set HK defined by HK is equal to small hk such that for all H belongs to H and K belongs to K. Okay. So now we'll show it with an example. It's called the product of two subgroups of H and K. For example, if H is equal to consist of this is equal to identity element and symmetry group, this symmetry group identity element and 1 2 and K consists of one identity element and 1 3. What is H? H is equal to 1 goes to 1, 2 goes to 2, 3 goes to identity element of the symmetry group, and 1 2 means 1 goes to 2, 2 goes to 1, and third element change, 3 element change. Similarly, K consists of 1 and 1 and 1 and consists of 1 2 3. That means second event 1 goes to 1, 2 goes to 2, 3 goes to 3, and this is 1 3 means 1 goes to 3, 3 goes to 2, and 2 means 6. Be a subgroup of a symmetric group S3 on 3 elements 1 2 3. These are two subgroups of S3 group. S3 group with 3 factorial means you have 3 factorial to 6 elements. So out of 3 we have taken these 2 elements. S3 we have discussed it in the symmetry in the chapter in the lecture of symmetry. Now HK will be, what will be HK? This is H belongs to H. HK. This is H, H2, K1, K2. H1, H1, K1, H2, H1, K2, H2, K1, H2, K2. This is equal to H1, K1, H1, K2, H2, K1, H2, K2. Now when you multiply them, it's equal to 1 goes to 1, 1 to 3, same element, the first row, domain element. So 1 goes to 1, 1 goes to 1, and 1 goes to 1, same 1 goes to 1. 2 goes to 2, 2 goes to 2, 3 goes to 3. Now 1 goes to 1, 1 goes to 1, and 1 goes to 3. 1 goes to 3, 1 3. 2 goes to 2, 2 goes to 2, 2 2. 3 goes to 3, 3 goes to 1, 3 1. Now this is equal to 1 goes to 2, 2 goes to 2, 1 2. This will be 1. 2 goes to 1, 1 goes to 1, 2 1. 3 goes to 3, 3 goes to 3, 3 3. Now 1 goes to 2, 2 goes to 2, 1 2. 2 goes to 1, 1 goes to 3, 2 3. 3 goes to 3, 3 goes to 1, 3 1. Like the product of this HK. If we write in symbolic form, it will be this I with the image set and the domain set both are same, then this is identity element. This is 1 goes to 1, 1 3 3 2, 1 3 3 1, 1 3 domain set. 1 2 2 1, 1 2 2 1, 1 2 2. This is 1 2 2 3 3 1, 1 2 3. 1 2 2 3 3 2 1. So what we have this. So HK is not a subgroup of the group S3. Why? Now I have taken the segment from this. This is HK. This is HK. H and K were subgroups, but the product may or may not be subgroup. So HK, we multiply. We take this element from HK. Belongs to HK. This belongs to HK, and we find the product of this element. 1 to 3, 1 to 2, 2 goes to 3, 3 goes to 1, 1 to 2, 2 goes to 3, 3 goes to 1. We find the product. 1 goes to 2, 2 goes to 3, 1 3. 2 goes to 3, 3 goes to 1. to 1. 3 goes to 1, 1 goes to 2. Now this element is 1, 1, 3, 3, 3 goes to 2, 1, 3, 2. 1 through 3. This does not belongs to HK. This is not even clear. So closure property HK, if closure property does not hold true in HK, you take an element of HK and the product of two elements of HK is not belong to HK. Means if one of the four axioms does not hold true, means that non-empty set is not a subgroup. It's not a group in itself, so this is not a subgroup. The subset has 3, so this is not a. If it does not hold true in HK, therefore HK is not a subgroup of S3. Similarly, we can do for KH. Symmetry KH, ultimate 1 to 1, 1 to 1, 2 goes to 3 goes to, this is equal to, this element is 1 goes to 2, 3, 3 goes to 1, 2, 2. This is the element is 1 goes to 1, 2 goes to 2, 3 goes to 3. This is 1. This element is of K, this element of K, this element of H. 1 goes to 2, 2 goes to 1, 3 same it is. When you multiply them, I with I with this same. When you try this with I, same. This with this, we got 1, 1, 3, 2. Now 1, 3, 2, this element is in KH, and we don't have this element in, we have 1, 2, 3, other three elements are same. Elements are same, but the last elements are not same. This implies if you multiply two subgroups, their multiplication is not always commutative. Now, our aim is to show that when will the product of two subgroups will be a group? Will be a subgroup. So, the first thing is if H and K are two subgroups of a group G, then HK, the product of H and K, is a subgroup of G if and only if HK is equal to KH. If you take two subgroups of a group, then their product will be subgroup if their product commutes. Their product commutes. So this is necessary part. Necessary part means this is true. Let this is true. We will prove that HK is equal to KH. Now let us suppose that necessary part is let H and K be given two subgroups of the group G such that HK is a subgroup of G. Now we need to prove that HK is equal to KH. What to prove? We prove HK is equal to KH and KH is equal to HK is subset of KH and KH is subset of HK. So we prove first part HK is a subset of KH. So let us take one element belongs to X belongs to HK. If X belongs to HK, but HK is given to be a subgroup. So inverse of that element also belongs to HK. HK is a subgroup. If we any subgroup, any subset of any group is a subgroup if it's to all the four axioms which are satisfied with the group, and binary composition is also same. Now this axiom is true. So if X inverse belongs to HK, let us suppose X inverse or X inverse is equal to belongs to HK means first element to H, definition of H product. First element to H and second element to K, so that HK, so that H to H and K, right? Now inverse of element also belongs to the subgroup. So inverse of this X inverse is equal to HK inverse is equal to K inverse, reversal order, K inverse, X inverse, H inverse. Sorry. Since H belongs to H and K belongs to K and HK are subgroups, therefore H inverse belongs to H, right? Because both are subgroups and K inverse of K. So inverse of element is X is equal to K inverse H inverse. This will be first element to K and second element to K. So therefore K inverse H inverse belongs to KH implies this first implies X belongs to, we have taken that X belongs to HK, we have shown that X belongs to KH, implies HK is subset of KH. Now in the second part will show that KH is subset of HK. So now we'll take element X belongs to this, X belongs to KH, any element of this subgroup HK, KH. So what type of this HK will be? What can be this X will be? X will be H belongs to H, K belongs to H. For some H belongs to H, K belongs to H. Right? For some product of the particular product of two subgroups. Now inverse of this, inverse H, inverse of H, inverse of H, we have taken H. This is not a subgroup. Any element we have taken element belongs to H, KH. Now inverse of this. Why we will find inverse? Because HK is a subgroup. So we are taking the element to the HK. So X belongs X is this, therefore X inverse will be equal to reverse order. X is equal to HK inverse, KH inverse, H inverse, K inverse. So H belongs to H, K belongs to H, this belongs to HK. H and K are subgroups because H and K are subgroups. So if H belongs to H, then H inverse also belongs to H. K belongs to K, then K also belongs to K. Therefore H inverse K belongs to H K. This implies X inverse belongs to HK. We have taken X belongs to KH. We have shown that X inverse belongs to HK. Now HK is a subgroup given. We are taking the problem with the given. Therefore, inverse of this will be belongs to HK. So inverse of X inverse is equal to X belongs to HK. So X belongs to KH. We have shown that X belongs to HK implies KH is subset of HK. Then this A and B implies HK is to KH. If HK are two subgroups of a group G, then their product HK will be a subgroup of G if their product computes. Next film is now sorry this is part, no subset part is suppose H and K are two subgroups of a group G such that HK is equal to KH. Our aim is to show that HK is a subgroup of G. G. So now we have to show a subgroup of G. We'll prove this with the help of a lemma. We'll show this. We will show it with the help of a lemma. That is, for all xy belongs to HK, xy inverse also belongs to HK. So for that, let xy. We're starting with the left hand side. Let xy belongs to HK. So what kind of the element HK will be? X and Y must be X will be of the type H1 K1 H1 K1, Y will be H2 K2, H1 H2 belongs to H and K1 K2 belongs to H, and both are subgroups. Therefore XY inverse, what will the value of XY inverse? It will be H1 K1 H2 K2 inverse. Reversal order holds true. This again equal to H2 K2 inverse is equal to K2 inverse H2 inverse. So H1 K1 K2 inverse K2 H2 inverse. So now K1 into K2 Shatil holds true. So holds true because H and K are subgroups. So K2 inverse K2 inverse will be how much? Because this belongs to H. So K is subgroup. Therefore, this is equal to E. H is K is subgroup. So this is equal to E, or we can take E, or we let us take this element. This is the K. This belongs to K because K is subgroup, and this belongs to H inverse also belongs to H. H is subgroup. Now we have taken this element. K1 K2 inverse into H2 inverse belongs to K. This belongs to H. Now this is equal to this belongs to K. This will touch. So K1 into K2 inverse, K1 into K2 inverse into H2 inverse belongs to, because this is equal, HK to KH. This also belongs to HK because HK is equal to KH. This is equal to HK. So if they belongs to KH, they also belongs to HK. If they belongs to, if K1 K2 inverse H2 inverse belongs to HK, means this product of these three numbers is of the type H3 belongs to H and K belongs to K. This type. Substitute the value of this K1 K2 inverse H2 inverse in this. So H inverse become H1 inverse H1 H2 into H3. H3 holds 2. So H1 into H3 into K3. Now this is the H is a subgroup. Therefore H1 into H2 equals the whole 2. This belongs to H and K3 belongs to K. So this implies this belongs to HK. So XY inverse belongs to HK for all XY belongs to HK. We have taken X, we had taken X and Y belongs to HK. We have shown that XY belongs to HK. Therefore, with the lemma shows HK is something for H. Next thing is if H and K are finite subgroups of the group G, then order of H into K is equal to order of H into order of K upon order of their intersection. So that if H and K are finite subgroups of group G, then order of the product is equal to product of their order divided by order of the intersection. So let's do this. H and K are finite subgroups. So product is here. We know that HK, they are finite. So we can find their product. We can find HK. What is the difference to HK? Product of HK is equal to H belongs to. This product to HK is equal to HK such that H belongs to H and K. Now, we are given two finite sets H and K. Let the intersection be. If you find the intersection, let they have x1, x2, so to xn elements. Okay, given to us, and they have finite number of elements, and we calculated the intersection, and the intersection is rolled here. Product is rolled here. Product is this is this, and they are finite. Let's suppose their order is equal to order of H is equal to R, and the order of K is equal to S. Because now, now let us take now HK, HK, HQ, H is root of HK. HK can be written as, because the common elements can be written in the HK can be H and K are subgroups. H and K are finite subgroups. Therefore, their intersection is also subgroup. So H intersection K is also a subgroup of G. So subgroup G means if we take X belongs to H intersection K, H intersection K. So and this is subgroup. Therefore, we can place we can write E identity element between H and K, and E can be replaced by Xi inverse. So now Schüttler holds true, and this can also written as HXI into XI, H subset of this belongs to HK. This belongs to HK. This belongs to HK for all I use one. So we have induced the intersection elements. Now, if they belongs to HK, this means HXI belongs to H and Xi inverse HK belongs to K. Thus HK is equal to HK can be written as HXI into Xi inverse into K belonging to HK for all isomer. That is, what does this imply? This implies HK can be written in at least n different ways. How many different ways? HK can be written in the number of times equal to the number of the elements in the intersection of the two sets. Now we will show that these are the only n ways that HK can be expressed as an element of HK. HK only n different ways. So for that we'll prove it by contradiction. Prove by contradiction if possible. Let HK have another representation H1 K1 be another representation of this. Beyond this, we have suppose one more representation of HK can be H1 K1. Now pre-multiplying by H inverse and post multiplying by K inverse this equality. So we got K H K inverse is equal to H inverse K. H K1 inverse is equal to H inverse K. This belongs to H intersection K. This belongs to H intersection K. Why do this one H intersection K? Because this is the H intersection K. This will be equal to, if X is equal to this, H is equal to H xi. So H is equal to H xi. So H is equal to H x H inverse I with X inverse. This implies if A belongs to H intersection K implies another representation in the set. So write in this form. Now now this will be equal to this and representation. So these two elements. This equal to, so this will be xi and this will be xi. Therefore, the intersection element क्या what are type they will be equal to shell xi. So this if they both belongs to xi intersection, they must be equal to xi. So xi and this is equal to xi for some xi belongs to this x intersection x intersection x intersection. This implies when we pre-multiply by h, this we got h1 is equal to h xi. When we post multiply this by this multiply by k, this multiply by from this we'll get h is equal to how much? This side this h is equal to h x inverse and h x inverse, and this will be equal to k1 is equal to x I inverse h. How will you get this? If we multiply this by h, got this equal to h1 equal to this. Now if we multiply this by x I inverse, this multiply by x I inverse. So I inverse is e, h inverse go to the denominator and will be there. So k is equal to k1 inverse k1 is equal to x I inverse into x inverse into k, x inverse into k. So now this h1 is equal to this. Thus hk is in the form h1 k1 is equal to h into xi x inverse into k is not the new representation. You'll get the same representation, same what we got here, this same representation for any element. Same representation. Hence, each element hk can be written in exactly and different ways. Also, h can be written in r ways because the set order of set h is equal to r, and k can be written in s ways because the order of k set is equal to s. Therefore, hk can be written as how many ways? Hk can be written as r into s upon n different ways. Common you can set out this part. So this what this implies, right? Order of hk segment of hk order of hk is into order of h into or k upon order of h. Now, currently based on this is if h and k are two subgroups of a group G such that G is equal to hk and h intersection h intersection k is equal to E, then order of G is equal to order of h into k. Since we are using this lemma, but you must have here two finite subsets. So now we can use this lemma here. Previous theorem. If this thing happen, then order of since order of G is equal to HK and H is E, and order of instruction, if H instruction K is equal to E, therefore order of H into K is equal to 1. So now substituting the order of G is equal to order of HK, order of H into K upon order of instruction, order of is 1, therefore this implies order of H G is equal to order of H K is equal to order of H into K. When will this happen? True. When will this happen? If the instruction have only identity element common. Now next story, if H and K are two subgroups of a group G such that order of H is greater than under root of order of G and order of K is greater than or under root of order of G, then order of H intersection K, H intersection K, H intersection K will be greater than 1. Since H and K are subgroup of G, H and K are subgroup of G, they are finite subgroup of G. Finite subgroup of G, finite subgroup of G, the subgroup G, therefore HK is a subset of G, HK subset of G, and order of, given that order of G will be greater than or equal to order of HK, order of G is equal to not greater than is equal to order of HK, because HK is G, and this is equal to order of H into order of K upon order of intersection, order of intersection, and this is equal to order of H, which substitute the value, is equal to under root of order of G into under root of order of G, order of G, therefore this is equal to order of G, order of G is equal to this, order of G is equal to cancel out, we take this with this is equal to this is equal to this. Now if cancel out the G from here, so what will happen? What will happen to this? How will this be greater than order of G? Oh, sorry, this is the, we have placed the number by smaller number, so this is the, so 1 will be greater than 1. Cancel out the conflict from this and this. 1 will be greater than this, implies order of middle cross present, order of HK implies order of H intersection K. Got this? Order of G is equal to this product. If that is from here, then substitute the value order of H is equal to greater than order of G, this is small, greater than the smaller number. So this thing will become greater than this. Order of HK will become greater than this. Order of G become greater than this. Or this is equal to root square, same, cancel out the conflict both sides, they are both numbers, so this comes out to 1 is greater than 1 upon order of H intersection K, cross multiplying, we got this, and this